Okay, so today we're going to talk about complex numbers. Complex numbers are an extension of the number system to include the imaginary unit. So the imaginary unit is called I and is defined to be the square root of -1. Now, multiples of I are called imaginary numbers. Imaginary. So for example, I, 2I, pi times I, e times I, these are all imaginary numbers. And numbers that have no imaginary component are called real numbers. So for example, 1, 2, pi, e, these are all real numbers because they have no imaginary component. And we can combine real and imaginary numbers together into complex numbers. So complex numbers have a real component, call it a, plus some multiple of the imaginary unit. So a plus bi. This is a complex number, and sometimes you'll see this denoted as a member of, this symbol epsilon means a member of the complex numbers. So a C with a little bar. This means all of the complex numbers. So now that we've seen a little bit about complex numbers, let's think about their algebra. So how do we manipulate these complex numbers? Algebra. So we can add complex numbers. So for example, a plus bi plus c plus di. This is simply the sum of the real and imaginary components. So this would be a plus c plus b plus d, lots of I. And we can multiply. So for example, a plus bi multiplied by c plus di. We can simply expand this out. So this is going to be ac plus adi plus bci plus bdi squared. And then we can use the fact that I squared equals -1 to simplify this into AC minus BD. So this is the real component of the multiplication, plus AD plus BC, lots of I. So this is the general formula for multiplying two complex numbers. So as an example, which I'll do here in blue, we can add, for example, 5 plus 7i to 2 plus I, and this quite simply by adding the real components and adding the complex components, this gives 7 plus 8i. And we can multiply these numbers, so 5 plus 7i multiplied by 2 plus I, this plugging into our formula here gives us 3 plus 19i. Okay, so the final operation that we've not introduced here is division. So what does it mean to divide, for example, a plus bi over c plus di? Well, before introducing this, it's useful to introduce a new type of number called the complex conjugate. So the complex conjugate of z is denoted z star. So if z were a plus bi, then z star, its complex conjugate, is denoted a minus bi. So it's the exact same as the original complex number, but with a sign reversal for the imaginary component. Here we've got a plus, here we've got a minus. Now the complex conjugate together with its original complex number form a conjugate pair, a complex conjugate pair. So z and z star together. And we can use our previous algebraic rules to figure out what z plus z star is. This is a plus bi plus a minus bi. So this is 2a, and you can see that this is a real number. Similarly, z minus z star is a plus bi minus a minus bi, which equals 2bi, which is imaginary. Excuse the handwriting. We can multiply z by z star to obtain a plus bi multiplied by a minus bi, and this, if you expand everything out, equals a squared plus b squared. Again, this is a real number. Now, the fact that this is a real number is very useful for complex division. It means that we can multiply, for example, the denominator of our fraction. So, for example, if we've divided 2 plus I by 1 plus 5i, we can multiply the top and the bottom of this fraction by the complex conjugate of the denominator, in this case 1 plus 5i. So the complex conjugate of 1 plus 5i is 1 minus 5i. And we can multiply the top and bottom of the fraction by this value and not change its value. And then we can use the fact, as we showed here, that the product of a complex conjugate pair is always real. This means that the denominator of our fraction is always real, so that we can then expand this out using our previous algebraic rules here to calculate the value of this fraction, which is 7 minus 9i over 1 plus 25, which, if we expand this out again, this is 7 over 26 minus 9 over 26i. So by using the complex conjugate, we can calculate the division of one complex number by another. So that in general, the division of complex numbers is given by, for example, if you were to calculate the division of w by z, where w and z are both complex numbers, this is equal to w times z star over z times z star. Okay, so now we can move on to some uses of complex numbers. Now, one use of complex numbers is to find the roots of polynomial equations. For example, the quadratic equation. The quadratic equation is, of course, a times z squared plus b times z plus c equal to 0. The solution of this equation is given by the quadratic formula, which is z equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now, without complex numbers, this surd here would give us some difficulties if b squared minus 4ac were less than 0. We would have no way of expressing this square root. However, when we allow complex numbers into the mix, this surd doesn't pose any problem at all. So this guarantees that the quadratic equation always has roots, and in fact it always has 2 roots. This is because of the fundamental theorem of algebra, which states that every nth degree polynomial has exactly n complex roots. So the fundamental theorem of algebra guarantees that we have two roots for this quadratic equation. This quadratic equation is second order because its highest power of x is a 2, it's a square, or in this case of z. And we require these complex roots to guarantee that these two roots exist. So every quadratic equation has two roots. Now these may be repeated roots. For example, they could be the same number, but they are two roots. We can call them alpha and beta, and we can express our original quadratic equation as the product of z minus alpha and z minus beta equals to 0. We can expand this out to obtain z squared minus alpha plus beta, z plus alpha beta equals to 0. Now this is one of the key uses of complex numbers. This guarantees that roots exist. So roots exist in the complex numbers, but not necessarily in the real numbers, which is denoted by r here with a little line next to it. So another key property of complex roots is given by the complex conjugate root theorem. Which states that if a polynomial has real roots, real coefficients. So these are the numbers that are in front of the variable of interest. So that would be a, b, and c here. These are the coefficients of the polynomial. If those numbers are real and alpha equals a plus bi is a root of the equation, then beta is given by the complex conjugate of alpha, which is a minus bi. So that is the other root, or it is another root of the equation. So, for example, if alpha were 7 plus 2i, and I knew that the equation had real coefficients, then by the complex conjugate root theorem, I know that beta is 7 minus 2i. Now, in the case of higher order polynomials, for example, the n equals 3 case, so this would be az cubed plus zz squared plus cz plus d equals to 0, then the complex conjugate root theorem still applies. This says that if any of the roots are complex, then another root of the equation will be its complex conjugate. So this gives us two options for what the roots are. Either all of the roots are real, so that would mean that alpha, beta, and gamma, the roots of the equation, are all members of the real numbers, or one of the roots is real, and the other two are complex conjugates. So that would be the case where alpha is a member of the real numbers, and beta and gamma are members of the complex numbers, where beta is the complex conjugate of the other roots. Alternatively, you could write gamma being the complex conjugate of beta here. It doesn't really make a difference. We can extend this further into the n equals 4 case. So this is a quartic equation. So this would be az to the 4 plus bz cubed plus cz squared plus dz plus e equal to 0. Note this is just a coefficient e, this isn't the Euler number e. So this has guaranteed to have roots alpha, beta, gamma and delta by the fundamental theorem of algebra. So these roots exist. And now we have three options for what kind of roots they are by the complex conjugate root theorem. Either all of them are real, or alpha and beta are real, whilst gamma and delta form a complex conjugate pair. So in this case, gamma would be delta star. Or in the third case, we have two sets of conjugate roots. So this would be alpha equal to beta star, and then again we would have another set of complex roots where gamma equals delta star. So this has been an introduction to complex numbers and their use in classifying and finding roots of equations. Hopefully that's been helpful.